All right, this is exam 3. I know a lot of you have emailed me that you're really nervous about this exam. A lot of you have said, oh my gosh, like it's online, like how's that going to change? I just want to kind of say, first read what's been posted on your Blackboard page already about this, and do take the practice quiz and stuff. What else did I want to note? Print out that supplementary sheet and put it with you on your side, so it is with you and you're not flitting up and back and forth, because yes, they're going to give it to you in the top, but I find that to be just very annoying. I took the practice exam and going back and up and down and stuff was just very annoying, and it was not my jam. So I would print it out, because I found that when I had it on my second computer, which I always keep on my desktop to answer all of your lovely emails, when I have it on there and being able to just look at that and then take the practice quiz, I did way better on the quiz as well, which shouldn't really be the correlation, but that's just how it worked. So that's like some mini advice tips. And then please know that there is a WebEx session tonight at 7 p.m. my time, so Indiana time. I had a lot of people try and join a session that I realized were on the West Coast, and I was like, it's not correct. So it's 7 p.m. my time, which I don't know what that means for everybody else, because you all are not just within the States. I have a lot of people in other places, so just find out what time that is for you, and if that does not work, then email me. I will be available on the 13th because your exam is on the 14th, so please, that Monday, just fill my inbox with questions. I will be happy to answer any last-minute panicky questions, so please feel free to do that. All right, let's move on. So we're ranking the following complex ions in order of increasing wavelength. So wavelength is inverse to energy. And energy is measured by the energy absorbed, which means how many electrons are unpaired. So the more unpaired electrons, the higher the energy and the lower the wavelength. So cobalt is a D9 element. So if I look at the elements up here, they're all cobalt, and they all have a charge on them. So already these complexes are charged. So I need to pull up my octahedral splitting diagram because they all have 6. And I noticed that this 3+ charge is not going to have any problems because H2O is neutral, so it has a 0 on it. All right, so that means that 6 times 0 will mean that cobalt has a +3 charge, and of those 9 electrons, -3, because electrons are negative, I'm going to have 6 electrons to play with. All right, so if I have 6 electrons to play with, I'm going to also note that H2O is a weak field ligand. So when I look here, it's relatively weak. And that means that in the octahedral diagram overall, it is going to fill as per Hund's rule and not be forced to pair together. It is instead going to fill all my orbitals, even the high spin sections, as so. And we have one unpaired. We have 4 unpaired and 1 paired electron. And again, now when we look at energy, that means it's going to have higher energy and a lower wavelength. All right. So when it has this sort of ideology, that's how we're going to apply it to the rest of them. I need to get rid of this pen. Cool. Okay. Now we move on. Now I have another octahedral complex with a -3 charge on it, but I notice that Cn actually has a -1 charge. So I have -3 plus 6 will give me +3 overall. So I'm going to write down +3 on here. And again, +3 with D9, again, gives me 6 electrons to play with. So I have 6 electrons to go. Good. You'll notice all of these are going to have very similar number of electrons. It is basically for me to kind of show you how to use the crystal field splitting energy diagram. So Cn is not only a strong one, but is the most strong of the ligands here. And so again, I can't enter that top part, so I'm going to fill the bottom and pair them all. All right, so these are all paired. Now I need to erase my pen again. Or sorry, to explain this better, this means it's going to have lower energy, because if they're all paired, then this has a low energy overall diagram, which means it's going to have a very high wavelength. And not only that, I would assume it's the highest wavelength, because it is the lowest energy, because it is the strongest ligand. All right, so I also has -1, 3-, that's +6, but it's a weak field ligand. Not only is it weak, it falls weaker than water, which will come up in our ordering of our elements. So again, this means that cobalt has a 3+ charge, and therefore we have 6 electrons to play with. Wonderful. I'm going to plug those 6 electrons in, and I know that they're going to fill as per Hund's rule. So I can fill in the upper orbitals as well. Again, because it's weak, but we have some literally 4 unpaired electrons, I'm going to note that it does have a relatively high energy and then low wavelength, but it is going to, in comparison to H2O, have a higher energy and lower wavelength because it is a weaker ligand. So be thinking about how these relate to each other in that spectrochemical series and where those fall. And then, where's my pen? Okay, now we look at this the bidentate one, and I note that ethylmethyldiamine is strong, and I know that it also is 0 in terms of charge. So then I note that the CO is 3+, and as we know and love, this means that it has an overall 3+ charge, so I have 6 electrons to play with. This is nothing new. I'm going to fill this in as per usual. Now, while I fill this in, I'm going to chat again. This is ethylmethyldiamine. Ethylmethyldiamine is strong, but it is weaker than CN. And because it's weaker than CN, it is going to have a higher wavelength because it will have a lower energy. But the lowest energy will be CN. So I'm going to note that here. CN is the strongest, and therefore will have the lowest energy, right? So that being the lowest energy will then have the highest wavelength. And then I have ethylmethyldiamine because it has a weaker energy and therefore a higher wavelength than H2O, because H2O was overall the energy is higher for H2O than it would be for ethylmethyldiamine. But I'll also note over here that my iodine is the weakest of the group, and therefore will have the highest energy and therefore lowest wavelength. Oh, I've switched up my arrows. I don't know why I did that. But yeah, the highest in that regard. Okay, moving on. Someone asked me something about nickel complexes, and they kind of noticed a trend, and they were like, why do all of them, when they're octahedral, have 2 unpaired electrons? But this is literally nickel 2+. So nickel 2+ is just the way that it fills. And that nickel 2+ becomes a D8 metal cation, and this means that in octahedral complexes it's always going to be paramagnetic, regardless of its ligands. But then as well, in 4 coordinate complexes, the tetrahedral tends to be high spin, while the square planar tends to be low spin. This is just how this works, but it's mostly because of how octahedral versus tetrahedral splitting diagrams are. In that the octahedral has 2 upper orbitals, while tetrahedral has 3 upper orbitals overall. So it's just how they split. Oh, whoops. Okay, so for this one, be sure when you're reading out these questions that you are able to write an equilibrium chemical equation. This is very important. Know what you are finding, especially with salts. All right, so I have this much salt. So I want to write down basically, what do I know? Because that is the point in what this is. So I really want to note what I know. I know the mass. I know the molar mass of sodium fluoride from the periodic table. I know the volume from the question, and I know Kb of the equation. And then I'm going to make an ice table, but I need a concentration. So I'm going to use that molar mass, use my overall molar ratio, very important. Always use molar ratios. And then, of course, volume to give me a molarity. I'm going to plug that into my ice table. Be sure to note the ice table does not have water in it because that is a liquid. And then I'm going to plug this into my Kb value. Now, I look here and I think, 0.95 is very much larger than -11. So when I go by the 5% rule, I'm definitely going to note that because -11, 10 to the -11 is much, much less than 5%, I can get rid of it. So I know that X then is 10 to the 3.65 times 10 to the minus 6. I plug that into POH values, because again, we're solving for OH minus, and that is not pH. So then I'm going to use POH plus pH equals 14 to get my pH value. So again, note what you're trying to find. Okay. Now, here's another exam question. When I think, what color? I think green's too bright. I don't really like green. It gives my eyes a headache. Let's do black. Black will be better. There it is. Okay. So I want a pH, but I'm given a solution, and again, I'm given a salt. This is different in that I know that my salt is a conjugate base. So my Ka isn't really necessary yet. But I do know that I'm going to need the Kb value overall. So let's see. If I know that, it's like, okay, well, a lot of people ask me, why am I seeing OH minus? And again, it's because a salt is a conjugate base in this case. So I'm finding overall Kb then. I'm not finding Ka. So I'm going to plug this in, 5% rule, but I do know that I need Kb to plug in, so I'm going to use that lovely Kb times Ka to get my Kb value here, and then I can plug that back into the top, algebra, find my X value. This is going to be OH minus, so again, that's POH, and then from POH, I plug that back in to get my pH value. There we go. I just want to show this because this is a common problem that I think a lot of you guys asked me. So I really want to make sure we had this in our belts before moving forward. Okay, next. Is there a way that Ka relates to pH? And someone was asking me this because they didn't want to do the ice table stuff. And it's like, well, if you're asked to do an ice table and if you're using Ka in general, you're not going to be able to not use an ice table. You do need to do that, especially when calculating pH, like I said before. However, there are problems they're going to ask you about a trend. And there is a trend that comes about from what Ka represents and how that relates to pH. So when Ka is increasing, this means overall that the dissociation is increasing. And we know that strong acids actually dissociate more. And what that means when they dissociate more is that being a stronger acid, the pH is going to decrease because strong acids have lower pHs. All right, and finally, this is our favorite type of question, and that has to do with splitting diagrams and then also ordering them in magnetism. So when I do that, I'm first going to start with titanium. Overall, I do the math, and I get 1 electron. Again, 0 for H2O. I'm not going to really go through that just because we know that. We know how to do this part. All right, I plug in 1. It doesn't matter if it's strong or weak because there's only 1 electron to work with. All right, rhenium. Now that's a D9 complex. Plug that through. I get 6 electrons overall with my math. Plug those in. Again, though, that CN is a strong field ligand, and so I know that all of them are going to be paired, aka diamagnetic. So I've already found the diamagnetic complex, and I know that this is going to be the least whenever I'm measuring them through. Good. I found what should be at the bottom when I'm doing my multiple choice. Manganese, I know I have 5, and I know H2O is a weak field ligand. So overall, these are all going to be unpaired. Okay, something paramagnetic, and I know it's more paramagnetic than the 1. So that means it's right now the most paramagnetic. And then I'm going to do Fe, which is also D5 because Cl is a weak field ligand. So when I plug these in, again, I get all of them unpaired, which I'm not sure how they'll word these, but I put this in here to note that they would technically be equal because they're all 5 unpaired. However, in general, because Cl is more weak than H2O, this would mean that, other way, my bad, wrong way. It would actually be the greatest then because it would be more paramagnetic because these electrons then can move even more freely amongst those 5 orbitals. So that's kind of how that works as the overall trend. Just as you saw before when we were describing the overall complexes before in in our complex ions by wavelength. Same idea there. Okay, I want to wrap up by talking about other things that I did not cover in this video, but are some things that you do need to know. Half equivalence point. Half equivalence point is when the pKa equals the pH. So if they give you a graph and they tell you what's the pKa and it's of a monoprotic acid, you need to be able to look at that titration graph and find the monoprotic acid, find that half equivalence point, and be able to say, okay, this is telling me the pH, and then I also know the pKa, because it might ask you for the pKa or it might ask you for the Ka, but in any regard, you should be able to find it. A weak diprotic acid is going to have 2 Ka values. You need to know how to make those 2 Ka values into 1 Ka value. They are multiplied together, okay? Monoprotic acids only have 1 Ka value. And then strong titration graphs do not have them. You can't derive them because there is no half equivalence point because it's a strong acid. There is no half equivalence point in the titration graph. But do be able to identify as well, because it might ask you, here's the graph. What is this a graph of? And you're gonna have to say it's a strong acid conjugate or titrated against a strong base. It's a weak monoprotic acid titrated against a strong base, etc. It's gonna go through all of these with you. So please be able to identify your graphs. This might come up on your exam. Also double check your molar ratios. If it's not 1-to-1, then you cannot use M1V1. You technically should not be using it anyway, but I understand that it's a nice calculation, but just know if it's not a 1-to-1 ratio, they will definitely mark you wrong and happily turn away all disputes. So don't use the 1-to-1, or don't use M1V1 unless you're absolutely certain it is a 1-to-1 mole ratio. And for diprotic acids, it is definitely not a 1-to-1 mole ratio. And then finally, like I said before, take the practice exam, be comfortable with the new format, be comfortable with inputting numeric answers, be comfortable with how they come across, be comfortable with how they come up. They're going to give them to you all at once, so you will be able to scroll back to other ones, and you will be able to view everything in total. And be sure that you have that supplementary information next to you at all times, so it makes it easier for you to then go through and find what you are looking for. All right, if there's anything else you want to talk about, find me this evening at 7 p.m. I will happily go through everything with you. I will happily sit with you guys for a while. I've carved that time out specifically to go through questions. So please come prepared for questions, and I don't mind if you just want to sit in and listen to everybody else's questions because you're not sure about what's going on. And then again, on Monday, I'm free all day. If you want to make a quick 15-minute WebEx session to ask a question, or if you want to email me, I will be very quick to respond because I know it's the day before the exam. Sunday, I will be unavailable because I have a large meeting, and also I'm preparing for another PhD thing that will be due on Monday, so I'm kind of going to be very tied up. I will be answering some questions, but I will not be as available on Sunday as I will be today and on Monday. So please make sure you understand that Sunday I will not be available, and I am sorry, but it's just that I've got something else to do. So apologies for that, but please email me on Monday. Please come to this WebEx session this evening, and also I'll be answering emails all day. All right.